Okay folks, in our last video we are looking at planar graphs and we are going to show that there are exactly 5 regular polyhedra. We're going to prove that. Okay, quite a nice, long, complicated problem. It's the last example under this heading. So we're going to look at the first case, case 1, where each face is a triangle. Okay, that's the first case we're going to prove. So we're going to say let there be f faces. We're fixing the number of faces, and from that we can say that the number of edges, we've seen this before, will be at most then 3 over 2 times the number of faces that we have. Okay, so if we bring in Euler's formula, from Euler we have the following, that V minus E plus F is equal to 2. So the number of vertices minus 3 over 2F, I'm just plugging that in there, plus F is equal to 2. I don't like the fraction, so I'm going to double up everything. 2V minus 3F plus 2F is equal to 4. So twice V will be, this is minus F, it goes over as a F, plus 4. So my vertices, number of vertices, will be half the number of faces plus 2. Okay, so I've got that to fall back onto. Now I'm going to say that each vertex, each of these vertices of this polyhedron, has a degree of k. So each vertex has degree k. Okay, and I'm going to use that now to find the number of edges. So the number of edges will be the number of faces multiplied by the number of vertices, but 2 vertices belongs to each edge. So I have to then halve that, because half of the vertices gives me the number of edges that I have. Okay folks, and now with that in our arsenal, we're going to say that this will be E is equal to 3 over 2F, which is equal to K times V over 2. Okay, and what do I have for V? I can say this is K, or half of K, times a half of F plus 2, because I have that for V. So this is sure, certainly you can see I'm just going to manipulate this formula. I'm going to continue with those 2 things. The half on each side cancel. So I've left 3F's, which is equal to, again, K over 2 times, oopsie, no, not K over 2, K times a half F plus 2. Remember that half cancelled with this half over there. Okay, I get K by itself. So from there, let me do it on the side here. K will be 3F divided by a half of F plus 2. I have an ugly complex fraction there. So I'm going to double the top, double the bottom to get rid of that. So I get 6F is over F plus 4 for the value of K. Now I need to look at what's going to happen to K, okay, as I increase or decrease the number of faces, etc. So if I look at this, 6F divided by F plus 4 is an increasing function. Okay, so the value will keep on increasing. Why is this happening? Because I'm only looking at positive integer values to replace F with. I cannot have minus 2 faces, okay, or minus 6 faces, or half a face. I have a face, okay, on my polyhedron. So because that is the case, K must be smaller than 6. Why does this happen? Now let's have a look. As I keep on increasing k, this 6f over f plus 4 has a horizontal asymptote at k equal to 6. Now you can look at that. Let me just quickly remind you, it's the limit when f approaches infinity, when there approaches an infinite number of faces. Okay, so k will be that, take that limit, you have 6f divided by f plus 4. Now if we divide this whole thing with f, the top and the bottom, we get the limit when f approaches infinity of 6 over 1 plus 4 over f. That becomes 0 and we have a result as 6. Now remember, we're working with integer values of f. So the only k values that we can have here is k is 3, 4 or 5. Those are the integers smaller than 6 and bigger than 3. Remember, what are we looking at? We're looking at triangular basis. So the minimum number of the edges that we can have here is indeed 3 to form that triangle. So if k is 3, what do we have? Well, if k is 3, it means that f is 4. So we have a tetrahedron. Now we will look at them just now. If k is 4, that means that f has to be 8. The number of faces is 8, which is an octahedron. Okay, and then the final one, if k is 5, we have 20 faces. Okay, and that is an icosahedron. Okay, so there are exactly 3 regular polyhedra with, now the key word here is regular, with triangular faces. Now let's quickly see, that's the first case. We've proved the first case. Okay, let's quickly see what they look like, and then we will look at the second case. Okay, so here I have the tetrahedron, the very first one. It's got 4 faces, f was 4, and then each of those have a triangle on its face. An octahedron, there was 8 faces, 1, 2, 3, 4, 5, 6, 7, 8, and that is what it would look like if you were to form an octahedron. And they're all regular. You can see those triangular faces are regular. The worst one is the icosahedron. Okay, there are a total of 20 faces. So if you open it up, this is what the net for the icosahedron is going to look like. Okay, there's only 3 of those regular polygons that have triangles as their faces. Okay, let's look at case number 2. Case 2, we're going to look, instead of a triangle, we're going to be using a square. So each face is a square. Okay, so what do we have? We have the number of edges being 4f divided by 2. Okay, so that gives me 2 f's. So the number of edges is double the number of faces in this case. Now that comes from the rule that you are already familiar with. So if I bring in Euler, the number of vertices minus the number of edges plus the number of faces has to be 2. What does that bring about? The vertices minus 2f, because E is 2f, plus an f is 2. So from that we can deduce that the number of vertices is the number of faces plus 2. Okay, counting the edges using a degree of k for each vertex. So each vertex, oopsie, that was a bit of a misspell, has k degree. Then we get the number of edges, which we already know is twice f, and that will be k times the number of vertices, which is f plus 2 halved. Remember, there's two vertices for each edge, so we halve them and we have the number of edges. Okay, so with that now I can get k by itself, so I'm going to use these two. K will then be 4f divided by f plus 2. Now if I look at the same here, as f is approaching an infinitely big integer number, the k value approaches 4. So there's a horizontal asymptote at 4. Okay, which means the largest that k can be in this case is indeed 3, which produces 6 faces. Okay, and for that we have a cube. Okay, if k is 3, we have f being 6. Okay, so let's see, you can make k 3 and calculate it over there. So we have a cube. So there is only one regular polyhedron with a square on each face, and that is the cube. Now I'm sure you know what it looks like, but in case you didn't, let me take you to the cube. There's the cube. It has 6 faces, and each of those faces is indeed a square. Let's look at the third case, case number 3. So for case 3, clearly we're going to look at the pentagon. I keep on putting 2 e's there. Each face is a pentagon. Okay, now if each face is a pentagon, the number of edges will be 5f divided by 2. Okay, the number of edges as related to the number of faces. Now if I take this into Euler's formula, the number of vertices will be the number of edges, which is 5 over 2f minus f plus 2. I just threw everything to the other side. So 2.5 minus 1 is 1.5. Okay, so it's 3 over 2f plus 2 is my number of vertices. Now if I equate those two, 5f over 2, so the number of edges being of degree k, obviously. Should not forget to bring in the idea of each vertex has a degree k. So each vertex has degree k. Then I have k times 3 over 2f plus 2 halved as my number of edges. Okay, if I now continue with these two, I have 5f, those two k's cancel, is equal to k times 3 over 2f plus 2, which makes k equal to 5f divided by 3 over 2f plus 2. I don't like this complex fraction, so I multiply it away by timesing the top with 2 and the bottom with 2. I get 10f over 3f plus 4. 10f is 3f plus 4. Now let's consider that. As f, which is a positive integer, approaches an infinitely big integer, then the k value that I have here is approaching 10 divided by 3 in this case. Okay, now 10 divided by 3 means that this must be smaller or equal to 3. Okay, so if k is 3, then we have an f value of 12. So that means there's 12 pentagons. 12 pentagons makes up a dodecahedron. Now, in case you didn't know what a dodecahedron looks like, it's a big word, so let me show you what a dodecahedron looks like. It is 12 pentagons sewn together to create the dodecahedron, which looks exactly like that on the screen. Okay, so now we need to move to case number 4. Now, case number 4, for case number 4, we're going to prove the following. For case 4, we're going to work with an n-gon, where the number n is bigger or equal to 6. Okay, so if we know this, then the number of edges will be n times the number of faces halved. By Euler, v minus e plus f is still 2, so the number of edges will equal nf over 2 minus f plus 2 if I just throw everything over to the other side. So this will give me, is it n over 2? Yeah, n over 2 went to the other side, and that's what I've got. So if I then take out f as a common factor, I have n over 2 minus 1 plus the 2 that was there in the initial stages. Okay, I could have then multiplied everything with 2. I think it's just going to look better. So let's double up. 2v equals nf minus 2f plus 4. So there we can remove n minus 2f plus 4. So 2v will bring about v as n over 2 divided by 2f plus 2 as my number of vertices. Okay, so now we have the number of vertices. Now we are again going to say each vertex has degree k. Okay, so what do we know? We know that nf over 2 will then be equal to k over 2 times. The vertices are halved for the number of edges. Okay, because 2 vertices make an edge. So k over 2 multiplied by what we have over here, which is a half n minus 2 times f plus 2. Now again we have a situation where those things cancel one another out. We're looking for the value of k. So what is k? K will be nf on the one side divided by all of this, a half n minus 2 times f plus 2. I double up the top, I double up the bottom because there's a complex fraction. So I have twice nf divided by n minus 2 times f plus 4 as the value of k. Now remember what we said here. Because f is an integer that's positive, as f approaches infinity, we have k approaching 2n divided by n minus 2. Okay, so what does it mean? It means k must be less than that. Now, when k, okay, so again, f approaches a very large integer value, k has to be smaller than 2n over n minus 2. Now, if we let n equal to 6, it would mean the following. It would mean that our k value must be smaller than 2 times 6 is 12 over 4, which is equal to 3. But now k cannot be smaller than 3, which means now the more that we increase the number of f, the lower, or the number of n rather, the lower this limit is going to be. Okay, so that tells us quite nicely that there are no other polyhedra. So the largest polyhedron that exists that is regular is a polyhedron that's made out of the pentagons. Now I hope that helped you folks. Please like the video and subscribe to the channel.